Have you ever stopped to wonder how a self-driving car spots a pedestrian? Or, how your phone instantly recognizes your face? Well, the magic behind all of that is a type of AI called a convolutional neural network, or a CNN. So today, we're going to build one right from the ground up so we can understand exactly how computers are learning to see our world. All right, here's our game plan. First, we'll tackle how computers even perceive an image in the first place. Then, we'll build the core engine. That's the convolution operation. After that, we'll see how to refine the features it finds, turn all of that into an actual prediction, and finally, we'll look at the entire blueprint from start to finish. So to kick things off, let's just ask the most basic question of all. When you look at a picture, you see objects, you see depth, context, it's all instant. But for a computer, it's a totally different story. What is it actually seeing? Well, the answer is kind of simple. It just sees numbers, a giant grid of numbers. And get this, for a color image, it's actually 3 of those grids, one for red, one for green, and one for blue, all stacked on top of each other. So the entire challenge of computer vision really boils down to this. How do you teach a machine to find meaningful patterns, things like edges, textures, and shapes, when all it has to work with is this sea of pixels? And that brings us to our first, and honestly, our most important building block, the convolution operation. This is really the heart and soul of the CNN. It's the engine room where the network starts to find some kind of meaning in that giant grid of numbers. The main tool we use here is something called a kernel, or sometimes it's called a filter. Just think of it like a tiny specialized magnifying glass. See, each kernel is just another small grid of numbers, but it's been trained to spot just one very specific, very simple pattern, like a vertical line, maybe a sharp corner, or a little patch with a certain color. So, how does this little magnifying glass actually work? Well, it's a really systematic scam. The kernel literally slides across the entire image from left to right, top to bottom, looking at one small patch of pixels at a time. And at each stop, it does a little math and creates a new image that we call a feature map.
Okay, let's make this real for a second. Look at the calculation here. The numbers inside the kernel are basically weights. So when we multiply them with the pixel values from the image patch and then add it all up, we get one single number. Now, if that number is high, it's like the network is screaming, hey, that simple feature I'm hunting for, like a vertical edge, it's right here. A low number just means, nope, nothing to see here. It's amazing that this one simple operation is how the network begins to see. But here's the thing. A CNN doesn't use just one filter. Oh no, it uses dozens, sometimes hundreds. So you can imagine one filter that's only looking for vertical edges, and another one that's looking for horizontal edges, and maybe a third for patches of green. Each one scans the image and creates its very own feature map. And all together, they give us this really rich, multi-layered view of what's inside that original picture. Okay, so the network has found a whole bunch of simple features, but that's just raw data, right? Now it has to refine and summarize what it's found. And this brings us to 2 really key steps: activation and pooling. First up, we apply something called an activation function, and a super popular one is called ReLU. All it does is take any negative numbers in our feature map and change them to 0. Now, that might sound almost too simple, but it's an absolutely critical step. It helps the network learn complex, real-world relationships, which are almost never just simple straight lines. It's kind of like letting the network decide which signals are important enough to pass on and which ones it should just ignore. Next up is pooling. So, imagine you have this super high-resolution feature map that tells you exactly where every tiny little edge is. That's a ton of data. A pooling layer comes in and shrinks this map down, summarizing regions of it to keep only the most vital information. This not only makes the network faster and more efficient, but it also makes it more robust. And there are a couple ways to do this. Max pooling is the most common one. It just looks at a little window of the feature map and keeps only the highest value. It's like a feature hunter. It's grabbing the absolute strongest signal of that feature in that little area. Average pooling, on the other hand, just takes the average value, which gives you a more smoothed out general summary. Okay, we've done it. We've found our features, we've refined them. Now for the payoff. How does the network take all of this information and turn it into a final prediction, like saying, that's a cat, or that's a dog? So before that final decision can be made, we have to change the data's format. Right now we've got this stack of 2D feature maps, right? The flattening step is exactly what it sounds like. It just unrolls all of them into one single long line of numbers. This is all about prepping the data for the network's brain, This long list of numbers is then fed into what we call a fully connected layer. And you can really think of this as the network's brain. In this layer, every single feature value we've detected is connected to every neuron. It's right here that the network finally learns the complex relationships between all those little features. It might learn, for example, that the presence of pointy ears plus whiskers plus fur texture all together, well, that strongly suggests the image has a cat in it.
So the final output layer gives us a set of raw scores for each possible thing it could be. And to make those scores easy for us humans to understand, we pass them through a special function called softmax. It does this clever little trick where it converts all those scores into a nice, clean set of probabilities that all add up to 100%. And that's it. That's the full journey, all the way from raw pixels to a final, confident prediction. Now let's see what this entire blueprint looks like when we actually go to build it with some code. What's so incredible is how these really complex ideas turn into pretty simple, readable code. You can literally see each step we just talked about. Here's our convolution, there's the pooling, the flattening, and the final decision layer. Seriously, building a neural network today is kind of like assembling with high-tech Legos. So after all that training, what does the output actually look like? Well, just like this. That softmax layer gives us this beautiful, clean bar chart. You can see that huge spike for cat, telling us the model is 92% confident that it is looking at a cat. Pretty cool, right? So what's the big idea here? What's the main takeaway? The real power of a CNN is that it learns a hierarchy of features. It's almost like how our own visual cortex works. The first layers learn to see really simple things like edges and colors. Then, the next layers combine those to recognize textures and simple shapes. Then, the deeper layers combine those to recognize parts of objects, like an eye or a wheel, until the very final layers can recognize entire complex objects. So we've gone from teaching computers to just see pixels to teaching them to recognize objects. And that leaves us with a final, pretty provocative thought to chew on for the future. Now that they can recognize, what should we teach them to understand next? Thanks for breaking it down with us today.